Hi. Well, today I'm really happy to have Pat Keys with me. Do you want to do a little intro of yourself?
Yeah, sure. My name is Pat Keys. I'm an assistant professor in the Department of Earth and Environment at Boston University. And I have been doing moisture recycling research since, gosh, 2010, I guess you could say,
Mm.
sort of in that world. My background is a kind of a real mixed bag. I have an undergraduate degree in biology from Willamette University. I took a couple of years off and then went back to school for a degree. I have a master's of science in civil engineering from the University of Washington with a focus on kind of water resources and climate change. Then I took a couple of years, not off, but away from academia, and I started an environmental consulting company called Keys Consulting Incorporated, super creative name. And we focused on climate change impacts, adaptation, resilience with clients all over the place, with projects all over the world. And then I realized I was still really curious about the world, and I had a chance to go back to get my PhD. And so I took it and I got my PhD in sustainability science at Stockholm University. And that sort of, after that, my family had sort of settled in Fort Collins, Colorado, and I was able to continue staying in academia. Sort of, I guess you could say I was still pretty curious about a lot of questions, so I was still able to do that. I was very fortunate in that regard. Um, and I was a research scientist at Colorado State, and then I moved into an assistant professor role. And then recently moved to Boston University. So that's like a real quick
Okay,
snapshot.
cool. And so moisture recycling also goes by other names, precipitation recycling and the small
Yeah,
water. Do you want to just say briefly what it is?
sure. So yeah, I mentioned moisture recycling earlier, and I guess I should preface that by saying my research is quite a bit broader than moisture recycling, but I've spent a lot of time in that world. And yeah, for me, the idea of moisture recycling is just the atmospheric water cycle. So it's the thinking about the sources of water on the surface of the earth. So that's evaporation, transpiration. It can be either from an ocean or a land surface. And so the moisture recycling part is understanding where it arises, where it travels through the atmosphere, and then where it falls out later as precipitation of some sort. I know some people define moisture recycling on a much more local scale or a regional scale or only on land or all sorts of things. So for me, though, I sort of take a pretty broad view, and it's just this idea if you're tracking and understanding sort of the sources and sinks of atmospheric moisture, um, you are probably thinking about moisture recycling in my mind.
Okay, cool. And did you get interested in this when you were doing your PhD at Stockholm?
No, so actually it goes back quite a bit further than that. So at the tail end of my master's degree at the University of Washington, I applied for and received a fellowship that would take me to a Scandinavian research institution for the final year of my master's degree. And I found the Stockholm Resilience Center. It was only 2 years old at the time. This is a resilience thinking institute associated with Stockholm University. And I found this and I reached out to, I want to say, 7 or 8 different researchers there. And one of them got back to me, and her name is Lena Gordon. And I essentially said, hey, I'm just interested in coming out there. I'm independently funded. Would you be willing to sort of sponsor my application? And Lena said, sure. So I went out there and I actually worked with a whole bunch of different people thinking about surface water. Actually, I upgraded a surface watershed model for that fellowship, but right at the very end, sort of, Lena and I started talking about this other project idea, which was instigated by a conversation Lena had had with a colleague of hers, Hubert Sevenai, in the Netherlands. And Hubert Sevenai's, at the time, master's student, Ruud van der Ent. And so Lena had said, hey, I know this guy, and he has a master's student that just had come out with this really cool paper on moisture recycling. And so we had this big plan to try and build a research team from sort of me and the Stockholm group, and then Hubert and Ruud in the Netherlands. And we talked. We actually were going to meet in the Netherlands, and then there was an SAS pilot strike that prevented us from traveling. So instead, Lena and I spent sort of that day mapping out a whole research proposal. And so that research proposal ended up getting submitted to the Swedish Science Foundation, sort of the equivalent of the NSF over in Sweden. Meanwhile, I went back to the United States. I started a consulting company, and one of the things that I did was actually some scientific research to support an initial precipitation shed piece of science study. And that project was in collaboration with Hubert Savenay and with Ruud van der Ent, who I know well. I should probably mention. I know you had him on the show in the past. And so really, I started working on moisture recycling then, around 2010. And I've continued working on it this whole time. So I've known Ruud since 2010, give or take. And yeah, been working with him pretty steadily. And let's see, that's the first paper where we sort of cooked up this idea of precipitation sheds, essentially trying to, how can we think about, in an analogous way to we think about surface watersheds, how can we think about sort of airborne sources of moisture, sources and sinks? And that's where we started playing with this idea. I actually still have the notebook somewhere where on some, at the time, Skype, Ruud and I were trying to talk about what would be the best name for this sort of unit. Is it a sky shed or a rain shed or something? And eventually we got this idea of a precipitation shed. It doesn't really matter what you call it. It's a source region of moisture. But the other day I found this notebook and I saw like all the names like crossed out, like, oh, we don't want that, we don't want that. As we were trying to think about what should we call this thing. And yeah, so I don't know if that's too much of an answer.
That's cool. That's cool. I like hearing stories about how words came into being, because basically you're defining a lexicon for a new kind of field. And
kind of, yeah.
When they came up with the word for Big Bang, first it had some really scientific, collapsing nuclear. I don't know what it was.
Sure.
It wasn't very catchy, and so by renaming it, actually made. The black hole. The Big Bang also had a different name, but yeah, they both had different names beginning, but they end up very catchy names. And so
sure.
I have heard people talking about the precipitation shed, so it's kind of cool to hear this backstory.
Right.
When Ruud van der
Well, and honestly, yeah, and it's I think the most important thing that in kind of looking back at that body of work a little bit is the idea of like, let's use this unit. Let's try and work with this unit in a spatial sense, because now it kind of permits talking more specifically about an area on the surface of the Earth that might be connected to some other place downwind. That was really the point, honestly, at the end of the day. So you can call it whatever you want. But the purpose was to try and see whether or not that was a reasonable thing to do. And that's actually what my PhD was really all about, was like, how reasonable is this approach? How useful is this idea? That's what my PhD ended up being on.
And the shed part is to make you think about the watershed, to kind of analogize. Is that the idea?
Sort of that, and also that it's shedding moisture, I guess. I don't know. Some people have said, oh, it really should have been the evaporation shed because it's shedding evaporation. I'm like, yeah, true. But at the end of the day, what we were really intending to focus on was sort of the sink, the precipitation. And so we wanted to understand what was the kind of upwind area, the upwind catchment, so to speak, that supported precipitation in a particular location. That's why, I mean, the naming conventions, like you say, like it's inventing a new lexicon, but at the same time, there's so many different names for this phenomena that it's not worth being precious about that per se. I would probably be much more interested in saying, well, are people using the source and sink idea more now? And I think they are.
Right. So the precipitation shed tells you the source of where your rainfall comes from. There's also one where, what's the word for where it's where?
Well, yeah, and this is something that Ruud coined in a paper that he wrote, I think in 2013 or something. And that was the evaporation shed. So that's where does a region's evaporation go? So you can think of, it's useful to think of a place sort of in the middle of a continent. So let's take Colorado, for example. So you can think of all the places that contribute moisture to Colorado. So that sort of set, if you drew a circle around it, that would be its precipitation shed, the places that supply Colorado with precipitation. And then if you drew, and then it's going to evaporate stuff and send it elsewhere. And all the elsewhere would be some, we would call that the evaporation shed. But again, some people say upwind regions, downwind regions, that's fine. I think for me, yeah, the tricky question is how do you draw a line? Like, how do you say like this area is inside, this area is outside, or how do you weight the importance of regions that are contributing moisture? Because ultimately, a lot of regions could be contributing tiny, tiny, infinitesimally small fractions of moisture. So at some point, you want to say, well, we're not really talking about those places. So which places are you talking about? And that gets to be pretty tricky. And I think that's also where this very hydrology oriented subject sort of butts right into sustainability science, which is very problem oriented, saying, well, what's the question that we're trying, like, what is the problem that we're grappling with? We're talking about land use change. We want to understand the consequences of land use change in this particular place. Well, then maybe whatever lines that you draw in terms of upwind and downwind source and sink regions might have to correspond in some way to that would matter to this problem that you're focusing on. Because hydrologically, you could just say, well, the entire planet is in some way contributing moisture, even in fractionally infinitesimally small amounts, or most of the planet. And so, well, that's not useful. So how do you make it useful?
Mm. So for Colorado, what would you say the precipitation shed for Colorado is, and what is the evaporation shed for Colorado?
That's sort of, I'm sort of cheating by picking that example because my master's student that just graduated just did that. So, what her work shows, and her name is Catherine Humphreys. She just finished her master's degree at Colorado State, and what she found is that the sources of moisture for Colorado. Well, then I should preface that by saying this is especially true for eastern Colorado, and especially the northeastern part of Colorado. A lot of it actually comes from kind of regional sources. So when I say regional, I mean within Colorado, I mean adjacent states. There's a pretty substantial contribution from the Gulf of Mexico, but also from the Pacific Ocean, also from the Gulf of Baja California, so that body of water. So there's a lot of both kind of aquatic or oceanic sources of moisture that make their way in sort of plumes of moisture towards Colorado, but also substantial continental sources as well.
And how much?
And I would actually like cite the paper, but she's submitting the paper sort of like this week, so I can't cite it yet.
How much does California contribute to Colorado's rain?
A little bit, some. And I should say again, I'm really speaking primarily about northeastern Colorado right now. But California would some. If only by virtue of the fact that it's evaporating and it's sort of, if the Pacific Ocean is making its way to Colorado, California is sort of in the way. Mm-hmm. And there was a cool study that was done years ago now by, can't remember the names now. It was Lowe and Famiglietti. Oh, yeah. Do you know that work?
Yeah, I've seen the name around, yeah.
And that one was, what they did is they looked at the Colorado River specifically, and it was looking at how, among other things, the paper looked at a lot of stuff, but among other things, the moisture that arises from much of the irrigation and sort of the lower watershed of the Colorado River, which is sort of this mass of canals and irrigation and sort of artificial infrastructure, you could say. A lot of that moisture then transports, or some of it transports back up to the headwaters of the Colorado River. So there's this circularity in the water cycle for the Colorado River to a certain degree, not completely by any means, but to a certain degree.
Mm. And what about Utah? Is there a lot of evaporation from Utah that ends up as rain?
A little bit, but Utah is a pretty dry place, as you know. So there's some evaporation from some of the bodies of water, and also from some of the higher altitude mountainous areas with forests and so forth. And that's true of the entire sort of quote unquote desert Southwest, is there are still lots of mountains, lots of forests at higher altitudes, and those end up kind of showing up pretty clearly as sources of moisture. They're not dominant by any means, but they do represent sources of moisture. I think a thing with moisture cycling, though, to remember is that for a given location, northeastern Colorado, Boston, wherever, Oregon, um, you could draw a line of where this the moisture coming from, but all those places are also contributing elsewhere, right? So it's not a one-to-one.
Right.
This is something where you have some, moisture's arising here, let's say in Boston, and it's going to travel elsewhere. Some fraction will go to a particular place, and maybe you care about that place, but we can't forget that it's also contributing to lots of places. So the diffuse character of this quantity, this topic, makes it a little bit trickier in some ways than say a watershed where there is a one-to-one. Like water flows down, it's not one-to-one, I shouldn't say that, but it's clearer on a watershed basis because some water drops and it can evaporate out of the watershed, it can infiltrate, or it can run off. um, and and so in some ways that is the topographic gradient provides almost like a different kind of container, you could say.
Right. And a river is basically just a one directional, you know.
Yeah, and I don't want to diminish that because like some climates, some climates are, evaporation dominated in some ways where, there's so much evaporation, or the energy budget is such that there's very little runoff. What falls as precipitation essentially re-evaporates. Plains ecosystems are good examples of that. There was some fantastic work, I'm going to forget the name now, that really dug into this, almost like archetypes of landscapes and how they partition evaporation, precipitation, and runoff as a way to sort of understand that water challenges are going to manifest in wildly different ways depending on the kind of which archetype you're in. If you are in a system where actually you're dominated by runoff versus evaporation, you're going to have a different set of challenges probably, for the most part, than a place that's dominated by evaporation with very little runoff. And I mean, it's not, in some ways you look at the map and be like, oh yeah, this makes sense. The places that are dominated by evaporation, in a lot of ways become sort of our rain-fed croplands. Places that are dominated by runoff are heavily managed by the Bureau and the Army Corps. And so like, it's not surprising in some ways, but it was still, I thought, a really interesting way to crack that question apart.
Mm.
I can't remember the citation off the top of my head, but.
And then the evaporation shed of Colorado, where is that?
Oh, that's something Kat didn't dig into actually.
Oh.
So I don't know for sure.
Mm-hmm.
Other people have started to look a little bit more and started to use some of those words actually, and so I wouldn't be surprised if somebody had, maybe not for Colorado per se, but maybe for like the middle of the continent. There was a really cool paper that was based on CESM, isotope-based water tracking, a series of papers. Harrington et al., I want to say, that used the isotope-enabled version of CESM, which is the Community Earth System model that's developed primarily out of NCAR in Boulder, the National Center for Atmospheric Research. And this isotope-enabled version allows essentially online water tracking while the model is running. They can sort of track moisture in different ways. And so there was some cool work that looked at North America and parceled it off into these different segments and looked at sort of the exchange of moisture among those segments, as well as disaggregating it from evaporation, interception, and transpiration to really tease out, well, what flux, part of the evaporative flux, is actually connecting these two places. Is it transpiration dominated, which tells you something about the importance of land use? Is it interception dominated, also land use, so forth? So land use, I should say, vegetation cover, not land use there, but yeah.
Mm. And do you want to explain a little bit about how isotopes help scientists track water experimentally?
Well, this is dangerously close to the edge of what I can talk about.
Okay.
I can say that I've tried to support some projects that use isotope-enabled models or are using isotope-based methods to do some analysis of sources of moisture. And a crude explanation would be something like the composition of the water changes as it moves inland from, say, an aquatic source, especially an oceanic source, and as it moves inland and precipitates and re-evaporates and precipitates and re-evaporates, the composition of that molecule of water actually changes such that you can sort of track the trajectory that it sort of follows based on sort of a gradient of the molecular composition. And this is something that is exploited by especially the paleoclimate world, because there's lots of sort of evidence in essentially biomass and other evidence from previous biomass and so forth, and the signature of the molecular composition in the rock strata itself, that you can go back in time millions of years and you can actually see how, or you can try and see how water would have flown inland, which tells you maybe something about the climate, tells you something about the configuration of the continents, tells you something about potentially even like seasonality, maybe not seasonality, but over longer time scales, changes in the hydrologic cycle. Yeah, I should back up. Definitely not seasonality, but long-term changes in the hydrologic cycle. I will say it's always funny to work with people that are doing that kind of work personally, in part because I'm using data for my moisture tracking model that is like hourly, right? Reanalysis data. This is climate data. It's sort of like quasi observations, gridded climate data at the hourly time step, and then the people using the isotopes are talking about stuff that's there could be 1,000 years between two data points, and in my mind I'm like, is that a problem? And they're like, it's fine. This is different worlds, different time scales, right? Like they think about data in a totally different way. And so it's fun. I mean, it's just it's fun to do that kind of work across, even though it sounds like from the outside, like my mom would look at it and be like, you guys are both scientists. What's the difference? But it's funny to kind of step outside of your little bubble, consider like a normal frame for data analysis, for example.
Yeah. It's kind of amazing that they've figured out all this stuff about millions of years ago about how water moved and the climate, just measuring the stable isotope, just because some water molecules are heavier than other water molecules, and the ratio.
Exactly right.
All this, and yeah, it's pretty amazing. And Ernest Lati, he pioneered, actually, I guess, figuring out that the Amazon was creating precipitation recycling by using isotopes. I think he was the first person to use it. So he actually proved that trees.
Oh, that's cool. I didn't know they were first.
Yeah. So the Colorado River itself, right? What would you say the precipitation shed for the Colorado River is?
Oh gosh, I actually did this analysis like 10 years ago. I can't remember now. I was just curious, and I had the data, and 10 years ago I was still a grad student, so I also had time. And so I dug into like essentially some of these basins that were in the news, so to speak, in the Western United States, the Columbia, the Colorado. I made this map. It never went anywhere. This is one of the many things that's sitting on some hard drive somewhere. I can't remember what Colorado's was. Take an entire basin. Oh, actually, but it did. Now I'm thinking about it. You're reminding me. This is another thing. Is like maybe this is just age, or maybe it's a whole variety of things. This is part of another paper. The trade wasn't like the signature part of a paper where I looked at the sources of megacity watersheds, essentially the precipitate beds for watersheds. And the Colorado was one of them. We can dig this up right now. I won't do that. I won't click around. That's weird to do on a podcast. But we can find out right now, or after the show.
Okay. Yeah, the reason I'm bringing up, because there's 7 states in the U.S. that depend on this water for their agriculture, for their people, their cities, and so it's a huge problem in the U.S. because it looks like we're draining the Colorado River, and there won't be enough water in 2 decades or 3 decades, and officials are at a loss of what to do. So my question is, can we restore some more of the rain in the precipitation shed to kind of increase the Colorado River?
This is such a tricky question. I would say that level of intervention would presume a way better understanding of the system than we actually have. And by that, I mean, we're just starting to I feel like we're just starting to get a handle on a sense of the variability, et cetera, associated with some of these kind of the flows of moisture. Atmospheric rivers as a research topic is not that old. Now, I mean, to some people, you'd be like, oh, it's been around for decades. And it's like, that's still not that old. And that's a critical component for understanding the major sort of sources, the major events that inject moisture into parts of the Colorado River Basin, if not, parts of basins around the world. And so that's one part. Another part is the fact that a major part is that we now have a moving target with climate change. So almost all the phenomena that we're talking about from an atmospheric science perspective that are going to matter for moisture recycling, changes in humidity, changes in prevailing wind patterns, storm tracks, et cetera, changes in temperature gradients, the fact that the land is drying out more quickly than the ocean, all this stuff is happening and matters for understanding moisture cycling. And depending on the decisions that society makes around its carbon, we could either be a lot warmer or a little warmer. And I would say we're just now starting to get good comprehensive studies on climate change, the way that different climate change scenarios will have different types of moisture recycling. So Ari Stahl has done a lot of this work, or has led, I shouldn't say he alone, but has led some work on this. And there's more coming down, coming out every year, you could say. But I think because we don't know which scenario of climate change we're going to be on. It's also like in general, climate change is changing the game of how we understand how moisture kind of moves around the planet. That trying to think about almost like strategic intervention in that system feels real tricky to me. And it's not to say that you shouldn't consider it, but I think it just the burden of what would be required in my mind to actually do something like that, to like execute a policy plan, would require quite a bit more than from the science than what we have now. That's not to say you couldn't do that science. I just think it would have to be quite a bit more robust than what we've got now, in part because there's so many degrees of uncertainty, degrees of freedom in the data, so many different ways of analyzing the question, and so many different ways that the system could change with climate change. So it's almost like, yeah, I mean, in a stationary climate, maybe it would definitely be easier to answer this question. In a changing climate, oof, that sounds way harder.
Yeah. So it's a complex question, but it also seems like so important. I mean, there's billions and billions of dollars at stake on the Colorado River. So
yeah,
maybe if.
But I think that I think they're non-intervention based. Like if we're talking about water and efficiency, et cetera, in the Colorado, oh man, way easier approaches. I mean, hydrologically speaking, to sort of approach that question than trying to develop a new land use strategy and somehow like turn the knob by like 5% one way or another, versus a whole other host of policies that could adjust the share of, say, agricultural land, municipal use, industrial use, et cetera, which would potentially free up far larger volumes of water than afforestation or reforestation, kind of the land use practice side. At least that's my instinct, is to be like, figure out, like, we know that there's a lot of water that's being used for things that, maybe that's not the best use. I'm not going to go ahead and say that because there's lots of people that would disagree with me angrily. But we should be asking some of those questions, I think, in part because those are clearer, more easily understood, more obvious, I would say, solutions, or at least responses to some of this scarcity.
Well, it's not either or. So
it's true. It's fair. It's not either or. It's not either or. But if we had to sequence the way we think about things.
Yeah, I mean, but if it's 5% or 10%, that's a huge amount of water difference.
Yeah, and I just drew that number out of the air. I don't know what the actual number is.
Literally out of the air. But restoring landscapes also has many other benefits.
True. Yes. No question.
not just water. So there could be multiple reasons to.
Absolutely. Yeah. That's an excellent point. I mean, from the perspective of the whole kind of basket of benefits that arise from rehabilitating a landscape, yeah, I mean, biodiversity benefits, you name it, so many other things, quality of life benefits for the people that live there, potentially. Yeah, lots of additional co-benefits.
Yeah, so I guess yeah, I was thinking that so it would be good to allocate some funds to study this. I feels like to put more money in the research direction to kind of look at this whole thing. And you have looked at a little bit, right, at mega cities and how much they can restore their water systems.
A little bit, yeah. So some of that work, I was with that paper. That was something I did during my PhD, the megacity precipitation sheds. In that paper, what I wanted to do was I was also trying to see, does this science of like moisture recycling matter for like the densest concentrations of humanity? Is there a link? Is it relevant? Should we be talking? Can we talk about those things together? Or is this just like not useful? So it was honestly really exploratory in that sense. And what in that paper, what we tried to do was to figure out, is there a way to talk about almost like the vulnerability of municipal water supplies for these megacities, that could arise from the rate of land use change, the amount of land use change in their sort of upwind source areas and their precipitation sheds, and a whole host of things, honestly. And it was really, as far as I know, there wasn't much else that had tried to do something like that, like to develop some sort of like multi data source vulnerability index, for the sort of precipitation shed analysis, and or not quite like this, I should say. And so in that sense, I would say that I think it shows that some cities are pretty resistant to upwind effects, in part because they're coming from the ocean for the most part. Their sources are coming from the ocean. So like humans can only really affect that through global climate change for the most part. And so, but some places are intensely reliant on terrestrial sources of moisture, and that in places that are experiencing pretty dramatic types of land use change. So there are places on the world that could be pretty exposed, pretty vulnerable. There are mega cities whose municipal water supplies, are pretty exposed to upwind change. But I would say the big caveat being like that was a very preliminary analysis. And yeah, if I was in one of those highly vulnerable cities, if I was in charge of water, I would probably say, oh gosh, I should make sure I'm aware of this and thinking about this, and maybe do our own studies, right?
So there's certain where the land use in the surrounding area upwind, like what you do with it, if you chop down the trees or whatever, will affect the rain in that cities.
I think so. I think that's fair to say. The amount of how much it affects, how it affects it's so variable in the sense that it depends on where you are on the planet. It depends on when you get your precipitation. It depends on what is your municipal water storage system. So that's something we actually considered in that megacity paper, was on a city by city basis. We sort of looked into, well, how robust is their kind of municipal infrastructure for storing, treating, transporting the water for their city? Is it a run of river pipe that they're just sticking a pipe in the river, and it's like if the river's low, they're low? Or do they have the good network of reservoirs? It's not land use by any means. For some places, also, so like the bigger, more extent your precipitation sheds, then you have kind of baked in resilience in a way, because it's going to be you've distributed your reliance on a much larger landscape, versus if you have a tiny precipitation shed, all things considered, then you do have more kind of an acute vulnerability potentially.
So which were the major cities you found that their rain did depend on the surrounding area?
Yeah, and so these were, I will say, we four that by now are vulnerable, but the caveat being that they had very large precipitation. So while they could be vulnerable, they also had large precipitation sheds, rather, which means that they have a larger, like it's still profuse in some ways. So, but the four cities were Karachi, Shanghai, Wuhan, and Qing. And so those four cities stood out as being particularly vulnerable across all of the different metrics. So there were a lot of different metrics.
Okay, so three
What'd you say?
or three of them are in China. Those cities are in China, right?
Three of them are in China. Yeah, exactly. Yeah. Um, and yeah, and so I mean, it's in some ways it's not a surprise to me, in part because there is a lot of land use change across Asia, and that's part of the analysis is what's the rate of land use change in some of these places. On that side of the Eurasian continent, the terrestrial sources are very high, and that was a kind of a factor, like how reliant are you on terrestrial versus oceanic sources. The more terrestrial your reliance, that sort of ticks up the potential vulnerability. So there were a lot of factors that I think contributed to that popping out as being more vulnerable. Yeah.
So the wind blows from Europe to Asia normally. I mean, it also changes directions.
Yeah, give or take.
Yeah. So that's why there's more rain in Asia that's dependent on other parts of Asia and Europe.
Yes. Yep. Yeah, I mean, yeah. In general, yeah, for sure.
And this
I think it. Yeah, sorry.
And this was part of your PhD work, or
this was sort of a. I think there were a couple times where I told my supervisor, I was like, "Hey, I want to work on this project," and she was sort of like, "I don't know about that one." I said, "Well, I'll keep working on this other stuff, but I'll just keep it like on the back burner, the side burner." Then some of those projects sort of bubbled up and were like, "Hey, it's here. What do we think?" And she was like, "Ah, okay, that's pretty cool."
And
so this was, yeah.
Has it gotten any attention from cities, this work that you're looking at cities and precipitation shed?
I mean, I don't remember getting much. This was back in 2018, so this was published in 2018. And so I don't remember much conversation around it. I think there might have been a couple news articles or something that picked it up, but no, I didn't have like conversations with like city planners or anything like that.
Yeah.
And I think I would have been wildly uncomfortable if I had those conversations, in part because I think that's not me doubting the validity of the science. It's more just saying this is one small part, right? When you're somebody who's in charge of water, you're thinking about like the science, even though it's the science, is still one small part of your decision-making criteria. Right. You've got constituents, you've got elections, you've got balancing budgets, you've got, governmental internal politics of, horse trading for different types of, you get this, I get that.
Right.
So, and I don't know anything about that stuff.
And I do think sometimes our research doesn't propagate. Like probably there'd be a lot of cities officials who are really concerned about water would be like, hey, we want more research into this. Like,
yeah, I mean, I think you're right. I think this is like an ongoing challenge for like all of science, especially for science like this, environmental sustainability type science, problem oriented, that's trying to address sort of real world questions, real world problems, challenges, but finding that conduit that connects that information and then finding a way to communicate it effectively beyond the academic nerd community is tough.
Right.
And I say academic nerd community in the fondest possible way.
Right. Do all these people working on moisture recycling and precipitation recycling, are there some efforts to try and spread the word about this?
I don't know. I'm not a part of anything that you mean beyond academia, so to speak.
Yeah, because I know, like, say, I just interviewed Lan Wang Erlandson.
Oh, yeah, Lan Wang Erlandson. Yeah.
The FAO, which is the United Nations.
Yeah, true.
About the precipitation recycling, how it affects agriculture.
Yeah. Yeah, and so I also work with Lan quite a lot. I joke sometimes that we're twins, like we were PhD twins, because we did our PhDs at the exact same time. We worked really closely together. We don't look anything alike, but uh, our research is like complementary. But yeah, she's right. So the FAO does have a strong interest in this, the Food and Agriculture Organization, and they are very stakeholder, decision maker facing. Like policy relevance is key for them. And they're producing a report as we speak, or editing a report, I should say, as we speak about the benefits of forests to agriculture. And a chapter on that in that report is looking at the kind of, you could say, the climate side, and a big part of that is thinking about moisture recycling. What does the science say? The science says different things depending on which part of the planet you're in, what kinds of forests you've got, what kinds of agriculture is there. But yeah, so that's a really good example of a pretty high level governance institution that is interested in this topic. And actually, I should mention that one of the funders for Kat's work, I mentioned Kat earlier, she had done this moisture recycling analysis for this northeastern Colorado. It was actually an analysis for a very extreme year. In 2023, we had the record-breaking precipitation events. And so the Colorado Water Conservation Board, a state-level agency, wanted to understand a bit more about that extreme year, and partially funded Kat's thesis. And so one of the deliverables for that thesis was essentially, where did that extreme rain come from? How can we understand that extreme rain in the context of, and it was all rain, I should say, or it was, rain and hail. How can we understand that in the context of past years? How different was it? Were the sources totally different? All of that. So that's another example of an institution that I think became aware of the possibility to ask this kind of question, in part because one of the faculty in the Department of Atmospheric Science at Colorado State, his name is Russ Schumacher. He's also the state climatologist. So he is having very much on the ground discussions with producers, so like agricultural producers in Colorado, about Colorado's climate. And he's engaged with policymakers at the state level, talking about Colorado's climate, not just climate change, but climate, variability, et cetera. Agriculture is a huge part of Colorado's economy, especially some local economies. And so so this is something that I think he shared this with that agency, and they said, oh, wow, okay, yeah, this would be interesting to understand. So I think you're right that there's a certain amount of, if you can share this, the fact that there is this kind of scientific possibility to understand this phenomena a little bit more broadly, there could be more interest.
And you've been doing work to frame this as an ecosystem service, right? The vegetation generated rain.
Yeah, I muted myself. I think there's a saw upstairs running. I don't know if you can hear that on your end. But yeah, another paper in my PhD, it sounds like all I've been doing was just living the glory days of my PhD. So one of the papers in my PhD was asking this question, sort of, can we frame moisture recycling as an ecosystem service? And if so, what does that look like? What would that mean? How would we do that? And it's good you mentioned Lon earlier, because Lon, as part of her PhD, had developed this evaporation model that simulated evaporation partitioning at the land surface. So evaporation is moisture, turning from liquid phase to gas phase, but it has there's lots of different ways that can happen. If water can fall on, say, a leaf, that's called interception, and if it re-evaporates from the surface of that leaf, that's been intercepted and then re-evaporated. If water falls to the soil and gets taken up by the tissues of the plant and then evaporated out the stomata, that's called transpiration. It functions differently. You can sort of, so you can simulate that. So you can, if you have land use data, soil data, precipitation, climate data, et cetera, you can simulate that partitioning. And so what I did is I worked with Lon to adapt that model called STEAM. And we had a version of STEAM that was sort of a intact current vegetation world and tracked moisture recycling in that world. And then we defoliated the landscape. We essentially turned it all into like a barren scrubland. And then we tracked moisture recycling to sort of get an envelope, like with current vegetation, how much moisture recycling do we get? And with barren vegetation, how much moisture recycling do you get? Now, it's not quite dune here, but it's like a scrub land. And then that envelope was our way of sort of capturing roughly, this is the added value that vegetation provides for moisture recycling. You remove the vegetation, you eliminate transpiration for the most part, you eliminate most interception. Water is repartitioned as runoff as opposed to passing back to the atmosphere. And so there's a lot that we can do differently in that study. But I think it was really useful providing kind of a first order estimate, a conservative estimate, I would argue, for the effect of vegetation on moisture recycling. To do like if you wanted to get more detailed, you'd use maybe a dynamic model, like an Earth system model, have different land surfaces in that Earth system model. Then you could get at a lot more of the dynamic processes, changes in the diurnal cycle, changes in seasonality, actual changes in the simulated winds, all sorts of things that we couldn't do with our sort of soft coupled version of that. But we were able to provide an envelope, and that envelope says that there are parts of the world that are very reliant on vegetation in its current form relative to other parts of the world. And it follows pretty similar patterns as terrestrial moisture recycling in general, not surprisingly. But there are parts of the world where there's not that much vegetation, so you don't get that much extra boost from removing vegetation.
Cool. And then
I would say, and actually just one final note, sorry, is that work actually has gotten a little bit more attention outside of, I would say, whatever my community is. I'm not sure what my community is, but whatever it is, there's been some interest from outside in that ecosystem service dimension. And so another scientist, Becky Chaplin Kramer, who has led a ton of ecosystem service work, she invited me to contribute sort of this data and a little bit more analysis to some work where she was trying to combine a multiple index of critical natural assets around the planet, with moisture recycling being one of those sort of critical natural assets, ecosystem services. And so that idea has gotten a little bit more traction and is still sort of ricocheting around, bouncing around. It's probably what has motivated the FAO to be a bit more interested in some ways, among other things. Like there's lots of other work being done in this space. So,
cool. Yeah, I think the ecosystem services framework helps certain organizations, maybe governmental groups to
right, for sure,
a bit more.
Yes.
And then you and Lan also did some work on social ecological modeling or something.
Yeah, and I don't think this made its way into my PhD. I think this was sort of ongoing work. Yeah, so what we wanted to try and do was, I think there's this idea, that's out there now that upwind land use elsewhere can affect precipitation in a different place, right? This is what we've been talking about this whole time. That land use change in one place affects precipitation elsewhere. And what Lon and I wanted to do in that paper was see if there's a back loop. Is there anything that connects the place that's receiving precipitation back to that upwind source region? But instead of thinking about it, water doesn't flow uphill per se, unless you've got a lot of pumps. Water flows uphill to money and all that, or uphill to power. But in general, like in a natural kind of ecological geophysical sense, we can think of how maybe a downstream location could be connected to an upstream location or an upwind location. And to really investigate that, we wanted to think about sort of social dynamics, economic dynamics, political dynamics. And when you start using that language in the context of an ecosystem service, you bump right into this concept of social ecological systems, SES, which are a way to study coupled human and natural environments. It draws a lot from the complexity community, complexity science community, thinking about how there are feedbacks that exist within these systems that lead to emergent phenomena, all sorts of stuff. James knows a lot more about that kind of stuff, and other complexity scientists, you could say. So what we want to do is we want to say, okay, if we think about moisture recycling in this context of a social ecological system, then the moisture recycling side is sort of part of the kind of ecological connection, a main feedback in some ways that ecosystems upwind are connected to the ecosystems downwind via the atmospheric water cycle. So how might these systems be connected back upwind? So we did a deep dive into a couple case studies in, I believe it's Bolivia. Oh gosh, I'm going to draw a blank now. I think
Wow.
it's Bolivia. I want to say West Africa. Um, gosh, why can't I think of the third one?
Mongolia?
What's that?
Was it Mongolia?
Oh yeah, yeah. I think that sounds right. Um, is that right? Gosh, I can't remember now. Anyway, what we tried to do is we said, okay, well, let's map the precipitation sheds for these locations, and that gives us the boundary in which to sort of consider the spatial scope of these social connections, economic connections, policy connections. Um, and this was really an exploratory paper in some ways. It was an attempt to sort of open up this conversation that was already, there were already other kind of spokes into the conversation, but from different communities. So there's a couple other communities. One's called sociohydrology and one's called hydrosociology. Sound the same, they're different. And so those communities have been talking about some of these more kind of atmospheric connections, but from their perspectives. So this was our attempt to try and link this, especially through social ecological systems lens. Um, and I'd say there's still a ton to do there. Lon has a PhD student who's working on this still that's really starting to dig into some of these social dynamics. I've got a couple grant proposals that have been submitted to try and dig into this phenomena more, in part because if some places do have much stronger social kind of back loops to their upwind areas, those are levers of change, right? So those are ways that those places are potentially tied into affecting their own precipitation, albeit through totally different mechanisms, policy mechanisms, economic mechanisms, trade mechanisms. So I'm really excited about that work. I think there's a ton left to do. So many questions, and almost all of them rely on, aside from funding, but rely on really deep interdisciplinary work to understand those systems, which me sort of wading into initially is good for generating an initial question or set of questions. But beyond that, you really have to start working with the experts in their respective disciplines.
Mm. Could you give me an example of what you mean by the social back loop that connects
Sure.
to?
So yeah, so like let's say that, you know, a patch of land upwind is forest. It's like a mosaic of forests and rangelands and croplands. It evaporates water, which falls downwind to a city, let's say. So let's say we've got this upwind land mosaic, falls as precipitation in, I don't know what we want to say, Montevideo. Let's just make it up. Okay, so in Uruguay. Um, and so, but then we could say, okay, well, does Uruguay buy products from that area upwind? Is its domestic consumption within Montevideo, I'm saying that right? Montevideo or Uruguay, right? Yeah.
Uh,
Anyway, um, anyway, um, is its economy locally dependent in any way on the products generated upwind? In a way, like it would be, its activity would be promoting or discouraging certain land use decisions, which are then affecting its
oh wow.
moisture. That's what I mean. And so you could understand that trying to disentangle that question is very complex. A lot of different ways of thinking about the connectivity. There's network science in there, there's economics in there, there's policy sciences in there, institutional science, there's even like history involved. And so that's why it's it's not an easy question to ask. In some ways, the biogeophysical side is simple by comparison, right? We take this gridded climate data, we ask this question, we answer it, we write a paper. But then to talk about what are the connections that are poorly documented, which do not fit any sort of grid structure, they don't follow physical laws. Like, how do we study that question to then connect it back? Part of the reason is the sort of a dream scenario would be then we could build a cool simulator to say this is how we could simulate change in an upwind area and its effects downwind. But if you think it's actually a social ecological system, some sort of complex adaptive system with feedbacks, then you have to be able to have the other part of that connection. Otherwise, it's like half of a simulator, right? Like you're only simulating half of the system. You're not simulating all of the other stuff that's connecting back to affect change. And if there are some really important slow or fast feedbacks, reinforcing feedbacks especially, you could get some really surprising outcomes If you yeah, there might be surprising outcomes out there that you can't capture with your like 50% simulator. I don't know if any of that's clear.
Yeah, that's good. So yeah, so it's kind of cool how you're bridging the people part with the ecological part. And usually people, scientists study one or the other, right? But
Right, yeah.
really is like, I mean, usually economists, they treat nature almost as a separate physical process, but actually you're
Yeah.
creating that they're actually, I mean, economics really is a subset, I think, of nature because people are a subset of nature.
You're gonna need a whole other podcast series for that one.
Right. Yeah. but yeah, it's interesting that you're using a complexity theory lens too, right? So a system and
Right.
systems, and you actually have a fondness for looking at things from a systems perspective, right? Is that, or do you want to say a little bit more about systems and complexity?
I would say, I mean, I don't do a ton of work through that lens, but yeah, I think actually most of my work is implicitly through a systems lens.
Hmm.
Um, I think in practice, I don't always articulate it that way. Um, that has a lot to do with where I got my PhD. I got my PhD at the Stockholm Resilience Center, Resilience. Everybody always thinks I say Brazilian. That's why I specify no resilience, not Brazilian Center. Um, and and that institute has a deep connection to something called systems ecology, which really came out of systems thinking, systems complexity science. And so a lot of my, I don't know, academic training, especially my formative PhD training, was infused with that sort of lens, that systems thinking lens. I actually taught a class on systems thinking, sort of a one-shot systems thinking course at CSU, which was a ton of fun to teach. It was such a cool class to teach. Really asking these undergrads to think deeply about sort of the systems that we're embedded in, what kinds of leverage points exist, et cetera. We used a book called Thinking in Systems that was written by Donella Meadows, that was published posthumously, but yeah, it was a really cool class. I'm not trying to like promote myself. I should say it was a cool class to teach. I
Mm.
think the students had fun. I had a lot of fun. Yeah.
Well, in economics, there's like, I mean, complexity talks about emergence, and in economics, you have emergence like the invisible hand, and eco
Hmm.
what's emergent behavior. So it's interesting when you're trying to tie the ecosystems with the sociology, and they're
Yeah.
seeing what emergent things are. And so you can play around, in complexity, you change the rules a little bit and you get really different emergence behavior. So maybe if you just change a little bit how the ecosystem connects to the sociology, you get very different behavior, maybe more favorable behavior.
Yeah. And I think there's been some really there. I think almost like all the ingredients are out there, scattered in different disciplines. I think a really strong, big opportunity is some of the advances in, I would say, network network science. It's like complex network science is probably a really good entry point for starting to wrap our heads around some of the social processes. So you could think about networks, social networks, political networks, economic networks, and from those networks, you can actually distill almost rules or kind of governing principles that make that network work, mathematical rules, I should say. And that's what would permit you to start to develop something like a simulator, is if you could translate what you observe in the data, in the networks that you find, into something that can be represented in numbers. And that's how then you can really connect that into some sort of simulation. And so there's a ton of work on complex networks. I mean, that's a whole massive field with subfields. Um, and there's even been some work on complex networks related to moisture recycling, to distill the moisture tracking findings into a complex network and then use that network to then ask and answer questions. And then the people have done similar things for people. And it's really just a matter of like, which networks do we need to develop and understand and sort of glue together to make the sort of representation of something that we can simulate and explore, change. And so, I mean, it's not for, I don't think it's for a lack of data per se. It's a lack of essentially finding the right people to work together to connect the dots that are already there.
Mm. Yeah, that's really interesting. The social system as a network and the moisture recycling as a network.
Yeah.
Because if you think about each tree as a node in this network, and it's deciding whether to transpire water up or not, and then also to bring water from the groundwater.
Yep.
So it's like all these nodes, and basically you're moving water between these nodes, kind of.
In a way.
Yeah. Cool. And then what's your current research, or what are you looking at these days?
On the moisture recycling side, one of the things I'm really interested in, it's actually, I always have an interest in the social dynamics side. I won't go into gory details, but it's actually really hard to find funding for that. It's very interdisciplinary. So you have to find really strongly interdisciplinary calls to support that kind of research. So that's sadly a bit on the back burner in some ways, until I can find resources to support that work. But the other thing that I'm really interested in is exploring a bit more how ecosystem stress, say evaporative stress, drought, et cetera, can propagate through moisture recycling to affect other places. So in other words, like if you're in Gabon in Africa, it gets a lot of moisture from the ocean, but also from East and Central Africa. So from Kenya, from the Congo Basin. And so if you're in Gabon, is your precipitation sensitive to the evaporative stress in East Africa? So like, are you seeing a signal in your variability, your seasonality, the actual magnitude of the amount of water that you're getting? Are you seeing any sort of signature or signal of evaporative stress or changes in evaporative stress as a result of that being transmitted through moisture cycling? And the reason I'm interested in that is in part, it's getting at a different aspect of sort of the complex and the kind of networked connectivity of these ecosystems to one another. I think some communities would say, oh, of course it is. But I'm not totally sure it's been demonstrated clearly in this way, for all the way from saying this is observed evaporative stress, maybe remotely sensed, so they're using satellite data, how that affects the historical transmission of moisture recycling, and then trying to then detect against a backdrop of a highly varying background signal changes in local moisture recycling that could be attributable upwind. And so that's something, and this is really coming from this idea of I want to also continue to understand sort of the teleconnected aspect over land, and through different sort of mediated by the ecosystems in multiple ways. That teleconnectivity among ecosystems and in very different places. This is also motivated in part because then it permits talking about the dependence of one place on the governance of another, where you can say this place is actually dependent in some ways on the way this place over here chooses to govern its land. I've done a little bit of work on governance of moisture recycling, and this is another way to sort of continue deepening that work through a slightly different lens, not just saying, hey, these places exchange moisture with one another, which is interesting in itself, but saying this place is actually somewhat dependent or sensitive to, exposed to the policy decisions in this place in this specific measurable way.
Right. Yeah. So if ecological stress in one location affects another location, then you would be interested in perhaps helping that other place have less ecological stress, because
I mean, it's honestly, it's like a route to cooperation, right?
Right.
It could be a way to say, hey, this is a problem for me. Looks like you're also having a problem. Hey, let's figure this out. Let's find a mutually beneficial solution to this challenge. And also because of sort of the diffuse reality of moisture recycling, it's also something that would lend itself more to sort of transboundary connections, transboundary cooperation.
Right.
It's rare that you would just have two countries next to each other. Canada and the United States are an exception of two giant countries that are next to each other, with few other countries sort of involved in their moisture recycling. Most countries, it's a total mess. And so as a result, you'd have to think about these sort of like consortiums of countries, transboundary relationships.
Right.
Yeah.
And this opens to also negotiation and game theory.
All sorts of other, yeah. Oh man, all sorts of other dimensions for sure.
Yeah. Cool. And then at Stockholm Resilience Center, I think were they the ones who pioneered this whole tipping point and planetary boundaries framework? And did you
I wasn't involved with I've only been peripherally involved with the planetary boundaries stuff. The report, the initial article, set two articles. It was sort of like a pair. Came out, I think, in, gosh, when was that? Was that 2009, 2010? And it was not necessarily the Resilience Center, but it was a bunch of scientists that met in Stockholm, though, or just outside of Stockholm. And then it was something like 30 scientists or something got together and talked this out. And that's where the planetary boundaries framing kind of, I think, was formalized. I'm sure it had been talked about for years before that. Tipping points as an idea has been around for ages. And so, but I mean, it has been sort of taken up, that concept of tipping points, like a critical threshold in a system beyond which you would be in a new system state. Um, and that idea has been taken up by, incorporated into the planetary boundaries framing. And I should say the planetary boundaries framing is this suggestion that there are specific thresholds within the Earth system that to cross those thresholds would begin a transition to a new Earth system state. And so what does that mean? Well, 20,000 years ago, we can talk about an ice age. That was like an Earth system state. And then because of variations in orbital mechanics of the Earth, the tilt of its axis and other things, Milankovitch cycles, we exited that ice age. And so that was two system states that the transition was quote unquote natural. But that's an example of two system states. And so we call this current time that humanity is in the Holocene, which is this last 15,000 years or so, maybe 10,000 years, I don't know. And then, and so when we talk about, when the planetary boundaries community talks about tipping points or other Earth system states, they're typically referring to a state that's different than the Holocene, the time that we find ourselves in, the time that like humanity is super well adapted to. And that to enter a different Earth system state could be something that is much hotter. I don't think very many people are suggesting that we're going to wind up in a much colder system state. It's usually some variation of a much hotter system state.
Mm-hmm.
And also that's just temperature. There's lots of other aspects of the Earth system than temperature. So that's just a really important one.
And moisture recycling or this precipitation recycling could play into this tipping point and this planetary boundary because.
So currently, so there is a hydrology or water tipping point, and the initial framing of it was based on surface water and sort of thresholds in surface water related to environmental flows, so the flows that are necessary for the ecosystems in a particular river to be sustained and to last and be resistant to change. That was adjusted in the last decade or so, probably more recently than that, I should say, to include quote unquote green water, so more kind of the evaporative side, the atmospheric side of water, thinking about all the landscapes that are not really where runoff is pretty marginal and where it's much more about precipitation and evaporation and really that exchange. So there is now a green water planetary boundary, essentially that other half of the water cycle, the one dominated by precipitation evaporation versus precipitation runoff. And that green water boundary has attempted to fold moisture recycling in, I would say. And I'm a co-author on a green water planetary boundary paper. I will say that the planetary boundaries are still a really evolving concept. And I think even the people that are on the inside, so to speak, that are really leading the charge would acknowledge that, you know, every year there's new insight about what the details of this or that planetary boundary are. And I think we can argue about whether this the right set of boundaries or not. But I think it's a reasonable representation of a lot of different key aspects of the Earth system. I think it's really different. It's really super, like the whole analysis of planetary boundaries is very reliant on, in many ways, things that haven't happened yet, phenomena that haven't happened, thresholds that maybe we haven't even observed and don't really know where they are, but we try and study via, as much as we can, via past evidence. Earth has been in many states through its whatever 3.5 billion year life. And so Um, there's lots of examples of different states. So we can use that. We can use models and simulations, et cetera, to understand what possible states might be out there. And what are the most important parts of the Earth system that we can sort of say, like, this is a distinguishable thing that we could cross as a threshold. But I would say that science is very much evolving on a yearly basis. For example, the plastics, essentially the novel entities planetary boundary, was, I won't say a black box at the outset, but it was not as well defined, and it's steadily become much better defined. Like, what do we mean by novel entities? Well, plastics have become an important one for thinking about the extensive plastic pollution around the planet at like every scale of the Earth system. And trying to now say, well, what are the consequences of that? All of the novel and synthetic entities in terms of pharmaceuticals, what does that mean? So there's still a ton of work to be done, but I would say that's it's this work. So I'm to wrap it up, like that work, my work is sort of connected to that, but I'm not like at the center of like all that work. I'm sort of dancing around the outskirts of some of it.
Cool.
I don't know what you want. I don't know what you want to end on. If there's a final question or something, or
yeah, I was just about to ask. Yeah, did you have any final maybe thing you might want to say to sum this all up?
oh gosh, a final thing to say. I think one thing, and this is hopefully not waxing too poetic, but one thing that has guided my research for moisture recycling, especially, but I would say it's true across the board for the most part, is to really find the questions that for me I've thought are unanswered, that are really interesting to me personally. And then in some ways, chasing them, even if some of the people that are around me are less excited. They're not if they said like, oh, that's a dumb question for this, that, or the other reason, I'll probably listen if I trust those people. But if they're not excited about it, but I am, I usually don't, I trust my excitement more. And so I think if I can leave you with one thing, something that would be valuable in my view is, if you're excited about chasing something, keep chasing it, because I think that there's so many more questions out there than we realize, that we haven't even realized we should be asking them. I think we have the sense that we've discovered everything, right? That every rock has been turned over, scraped clean, that there's nothing yet left to do. And that's like hilariously not true.
Yeah.
Especially in this thorny, challenging area of thinking about the intersection of anything physical, natural, Earth system, ecosystem, hydrologically related, and people. We still think that we've scraped the rock clean. We haven't. So like, if you're interested and curious and excited about something, keep chasing it. Even if you have to put it on like, not even the back burner, like the warming section of your stovetop that's like barely keeping it warm. Don't lose it, right? I've had to do that multiple times in my career, where I have to set something aside to work on something else for whatever reason. But don't forget that that's there, because that could be the biggest thing that you contribute to like our understanding of the world.
Right.
So yeah.
Yeah, cool. Yeah, and there are a lot of questions in moisture recycling out there still.
So many questions.
Yeah, cool. Well, thank you so much. I really appreciate it.
Yeah, you bet. Yeah, this has been fun.